Welcome back to the series of lectures on high-performance scientific computing. In this video, we will review certain concepts related to distributed memory machines and how to program distributed memory machines. We will introduce the message passing interface, which is a standardized and portable application programming interface for distributed memory parallel machines. It is extensively used in high-performance computing applications, and it essentially enables programming of distributed machines which are built by assembling several computational nodes together. A distributed memory machine effectively is a combination of several single computing nodes. The MPI interface essentially enables communication between the different processes that are running on different nodes of this cluster. It is supported by libraries like MPICH, OpenMPI, or the Intel MPI libraries. So first of all, why do we use MPI, or the message passing interface? It enables the parallel computing on distributed memory systems. It can support extremely large scale computations beyond a single machine, and we can extend calculation to hundreds, if not hundreds of thousands of compute nodes. We have explicit control over the communication and synchronization of running this code across these hundreds of thousands of processors. And this is a standardized application programming interface which has cross-platform compatibility. What do I mean by that? Is that once I write an MPI code for a particular distributed memory machine, usually if the standard is installed and applicable on another distributed memory machine, you should be able to port this code. So you can take your code from a small development cluster which has a few compute nodes to something extremely large, and you can scale the problem effectively. What is the MPI execution model? So in the MPI execution model, multiple processes or multiple individual programs which are launched, and each of it has its own memory space. Each of it works on a different bit of the problem or a different bit of the data. Communication is done via message passing. Processes can run on multiple machines which are then connected by any sort of network. This network could be a simple Wi-Fi network, could be something much more fancy like an InfiniBand network if you want high communication bandwidth. Typically, you launch a program using something called as an MPI run or an MPI execute command, which initializes the program on these different distributed nodes. First, to use MPI, you need to install an MPI implementation, something like an OpenMPI or MPICH. And then to compile this program, you need to use a special function called, or rather special program called MPI-CC. MPI-CC basically wraps the existing C compiler and makes it recognize the MPI communication functions. So think of it as a layer which sits on top of your existing compiler. So when you have an MPI function which is being called by the program, then the appropriate library function is called for doing the requisite message passing. So in this case, we are compiling the program.c and putting it into an output file called program. And when we want to run the MPI program with multiple processes, we have to use the MPI run or the MPI execute command, and we need to specify the number of processes that we want to initialize and then give it to the program. Then the MPI function calls will be recognized in that environment and appropriately executed. So the typical MPI program structure will include something like this. An MPI header file, which obviously is required to reference the MPI functions correctly. You will need to initialize the MPI environment using the MPI init function, which gives the arguments of the total number of processors or the number of processes that need to be started, and also in many cases where these processes need to be started, i.e. what machines they are supposed to get started. If you do this, the program then knows where it needs to go and execute. And to close out the program, you need to have a finalize function call, which ends all the programs smoothly and does a synchronization. Each MPI program which is executing independently on each node needs to know its identity, and also it needs to know what is the size of the world that is there. So MPI com rank and MPI com size are the two functions which report back what is the individual rank and what is the size of the total MPI world, or i.e. how many MPI processes are running out there. So the basic MPI functions are MPI init, initializing the MPI environment, MPI finalize, which terminates the MPI execution, MPI communication size, which gets the total number of processes, MPI communication rank, which gets the rank or the ID of a particular process, and then finally you have the MPI send and the MPI receives, which basically sends and receives messages and forms the building blocks of every other MPI function. So you can do point-to-point communication with MPI, which is a blocking send and a blocking receive. That is, I can send one bit of data using the MPI send command, where I'm sending what data is present at the address of the variable data. In this case, we're saying it's an integer. We're giving it a destination. We're giving it a tag. Similarly, correspondingly, for that particular send, there has to be a receive. And until the pair of send and receives is done, the program will not proceed ahead. So this is called a blocking send and receive. But sometimes you can do a non-blocking communication, where I can do an iSend and similarly have a non-blocking receive. So where the program, once it does the send, goes ahead and does any sort of computation that it requires further down the program. So we need to sort out synchronization issues if you're using non-blocking communication. Then we have collective communication, where we need to broadcast data, for example. So we use the MPI broadcast or MPI bcast function, which will basically take one data member or any large set of data members and broadcast it to all other processes within one command. So instead of writing several MPI send receives together, you can just use a single function to copy that data to everybody. You have the MPI reduce function, which reduces the data using operators such as sum, product, minimum, maximum across different processes. You also have MPI all reduce, which works like MPI reduce but stores the result of this data in all processes. MPI reduce will do the reduction only in one process. MPI scatter will distribute distinct parts of an array to different processes. MPI gather will do the reverse of collecting results from all processes into one. For example, you can look at this MPI broadcast function. So here I'm broadcasting the variable data, which is a single integer, from the root to the rest of the world. We also need to do MPI synchronization. As these are distinct codes which are running on distinct parts of the problem on distinct nodes, obviously they're going to run at different speeds. So at many times we would want to have a synchronization points where all the MPI processes have finished their tasks up to a certain point and then can proceed to the rest of the program only if they have all finished that particular tasks. For that, we use the MPI barrier function. Once you put an MPI barrier, this ensures that all processes will reach that particular point before proceeding to the next part of the code. This is very useful for ensuring data consistency. Here are a few case studies. We had talked about the parallel matrix multiplication, where we used a combination of MPI scatter, MPI broadcast, and then MPI gather. Each process computes each part of the matrix multiplication and then gathers these results. We had also talked about distributed image processing, where the processes work on separate parts of an image for whatever filtering, edge detection, blurring, so on and so forth. We again used MPI scatter to divide the image and then MPI gather at the end to combine the results. This is optimal for processing time for large images and large data sets. Similarly, weather simulation can use MPI models where multiple processors compute weather models on different regions of the region of interest. You periodically exchange information at the boundary between the neighboring processes. For example, if you want to do weather simulation over the entire Indian subcontinent, we can geographically divide the Indian subcontinent into several parts. Each MPI process will then compute its individual region and periodically exchange information related to pressure, humidity, rainfall, so on and so forth between the neighboring processes. You can achieve speed up by distributing the computational workload evenly amongst these processes. We also talked about debugging and profiling MPI programs by using the MPI WTime function, where we looked at how to time up MPI program. We also talked about tools like Valgrind, which allows you to figure out what is going on internally in a program to see where the memory misses are, where things are going wrong. We used MPI profiling tools like MPIP, Tau, Intel, and trace analyzers. To optimize MPI performance, one thing we need to do is always minimize communication overhead, because the more communication that you do, the slower the program is, the more are the bottlenecks. So it's always advisable to use non-blocking communication like MPI send, I send, and MPI I receive. But we have to be careful to see whether the data has actually been received when you finally want to use it. We should also optimize the collective operations, and we need to talk about efficient data partitioning for balancing the workload. We had talked about how to efficiently partition the data using tools like Metis. So here are the fundamental differences between MPI versus OpenMP, which we just discussed. In OpenMP, we have a shared memory model. In MPI, we have a distributed memory model. So that typically means the size limit or the number of processing cores limit in OpenMP is limited to what hardware we have. Whereas in MPI, we do not have such theoretical upper limits. We can add as many processors as we want going ahead. The communication in OpenMP is implicit when the variable and data are being shared. Whereas in MPI, you need to explicitly send the data because each program has its own memory space. In OpenMP, the memory space is shared as the name suggests, so I can directly reference any data that I want. OpenMP obviously is limited to a single machine. MPI scales across clusters. OpenMP is relatively easier to use. It just uses compiler directives. Usually you can take a serial code and introduce the OpenMP directives within a few hours and get some moderate to good speed up. MPI is a little bit more complex because we are doing explicit message passing. We need to redesign the entire algorithm a little bit. We need to introduce the concept of partitioning the problem explicitly using tools like Metis, and hence it becomes more complex. So in summary, MPI enables parallel programming on a distributed memory machine. It supports point-to-point and collective communication and is effective for HPC applications such as large simulations and large-scale computations. Thank you.